Hello and welcome. This is the second video on pressure, and we're going to be deriving an expression for pressure as a function of depth for constant density liquids and in a region with constant local gravity. It's a pretty simple derivation that's really helpful for liquids, and it will serve as a motivator for a lot of these other applications that we'll be talking uh, about the hydraulic lift and also buoyancy. So let's get started. When we Sorry about that. When we derive this expression, this is kind of the setup, and this is how a lot of these pressure derivations go, is that we have to imagine that we're in a container of liquid, right, that's starting, say, right, that's filled, and we want to start the liquid at a coordinate z equals 0, and we want to consider part of a slab of this liquid. And now the top of this slab is at a location z, and the part of this below it is at a location z plus dz. That's how these calculus derivations go. The liquid has a density of rho, constant density rho, and well, this is kind of a cross-section of really a three-dimensional thing. So the slab has an area, it has an area of A, and we're going to include that. Oops. Okay, and so what we're going to do now is do forces. We just do a free body diagram on this little slab, this little chunk of fluid. Sometimes we call it a parcel. What are all the forces acting on this fluid? Well, there's obviously gravity. What's the expression for the gravitational force acting on it? It depends on the mass and also the free fall constant. The mass is something that's going to have a weird form. In addition, at every one of these edges, because you have to imagine this little slab here is kind of a three-dimensional object, right? So every one of these parts of the fluid has a pressure force acting on it, right? Every section, every point of the slab has a pressure that's being exerted on it by the fluid around it, because pressure is just a force everywhere on the object. The ones on the side all cancel out, but the ones on the top and the bottom do not. And so the free body diagram for that slab is going to become, we've got a downward F sub G. We have a force from the top, pressure, the force from the pressure above, which instead of writing it just as force, we're going to write it as P times A. Okay, that's going to be the force due to the fluid pushing down on it. And then what about above it? We're going to have a force from the fluid above it. That's going to be P plus dP times A. Okay, because how we derive these functional relationships is we don't know what the change in the pressure is. We're using this derivation to try and justify the expression for how the pressure changes. So we're just writing it as just P plus dP. So now we can write this out as an equation using Newton's first law. Obviously, F net is equal to 0. So what is an expression for Fg? Well, Fg is just, like I said, mass times free fall, but the expression for mass is just going to be density times volume. And so we've got, but the volume, what's the volume of this little chunk right here? The volume of this little chunk is the area A times dz. And so we can write that out as rho A dz. That's the expression for the mass of the little particle. So you multiply that times gravity times free fall constant, and then you have to add the force due to the pressure above it. So it'll be P times A. Right? These technically should have minus signs, but we're just doing magnitudes here. And that's going to equal P plus dP times A. Okay, so on the right-hand side of this equation, we have the pressure due to the fluid below pushing up. And on the left-hand side, we have the two forces that are either pushing or pulling the object down further into the liquid. Now, keep in mind, this is happening everywhere in the liquid. This isn't causing this little chunk of water to move around the fluid. This is just the forces that it feels in equilibrium. So what are the things that we can cancel about this? Well, first of all, if you factor out if you distribute the A on the right sides of the equation, you see that both sides have a factor of P times A. So we can just go ahead and cancel that. And you also see that everything has a factor of area itself. So we can cancel the A. So when we do all that cancellations, what are we left with? We're left with density times free fall times dz equals dp. And this is our expression for the rate of change of the pressure, not the rate of change of pressure, but how the pressure changes when you go deeper, right? The change in pressure is a positive increase in this factor of density times free fall. And so we have a little equation here that we can integrate. If we go back to the original picture here, we had this liquid where we assumed that the top of it was connected to the atmosphere. So what we say then at z equals 0, right, the pressure at z equals 0 is just usually atmospheric pressure. But it doesn't have to be that specific value because we just need some initial value. So let's integrate both sides. We're going to integrate the left-hand side from 0 to z, and we're going to integrate the right-hand side from atmospheric pressure to the new pressure. Right? And then when you do that, you need these dummy variables for z and p. And so the integral is easy enough to do. It's not a big deal. So you're just integrating dz, which is z. I'm just trying to make that a little bit formal. So what we get when we integrate this equation is we're going to get rho gz equals the pressure at a specific time minus this initial value. And so we can rearrange this a little bit to get the expression for pressure as a function of depth. It's going to be P as a function of Z is the initial value at the very top plus this increased value. There we go. And that's your expression for pressure as a function of depth. A couple things to notice about this equation. This is using a coordinate system where Z does point downward, increasing, where it's getting more positive. If it was a negative, if we were using the typical coordinate system where up away from the Earth is positive, then we would have to do a minus sign. But that's just coordinates. So this is assuming a constant density in the liquid, and it's assuming a constant gravity. Both of those conditions can be changed, and we can get a more precise estimate. This equation works for fluids, oils, and liquid mercury, and different alcohols, and any different solutions, and especially water, in containers that have everyday sizes. But it doesn't work for depths that are hundreds or thousands of meters deep. For instance, the oceans, the pressures in the ocean, well, the density increases. So the density is not constant. So that's actually the pressure inside the ocean is actually going to increase at greater than the depth. It's going to be, you can assume that it's, maybe for large enough depths, it increases at maybe the depth squared, z squared, for instance. Since the density of water increases slightly the further down you go. Another interesting result is when gravity isn't constant. When gravity is not constant, then you can talk about how the pressure increases inside the Earth and also inside the sun. And those increases in pressure will get, not only do liquids melt into kind of gases, but the things that make up the atoms themselves start to melt away from one another, like protons and neutrons. They turn into kind of nuclear matter. So it's really interesting how pressure changes. This concludes this video on pressure versus depth. In the next video, we will consider the applications of it specifically to the hydraulic lift and also buoyancy. So thanks for your time.